All right, so I told a couple of students in my office hour that we'd finished chapter 10. I told them this yesterday. Then last night I was looking at chapter 10 and 9, and I thought, I'll just do 9. There's still enough substance in 9 that it's worth mastering well rather than going through quickly. Okay, so a topic that comes up from time to time in chapter 9 is that of a p-value. It's the smallest significance level, or the smallest value of alpha, at which the null hypothesis is rejected. So alpha is a probability. It's a number between 0 and 1. If alpha is, what is alpha again? It's a probability that H naught is rejected when, in fact, H naught is the real situation. So you pick alpha in advance, decide on an alpha, and then you have a test statistic. Like the test statistic maybe should be large. If it's large, then H naught is rejected. So this would be the probability that the test statistic is large under the null hypothesis or null distribution. If alpha is really big, do you tend to reject the null hypothesis more or less? More. If alpha is 1, how often would you reject the null hypothesis? All the time, right? If alpha is a half, you would reject it half the time, right? If alpha is a fourth, you reject it a fourth of the time. So you get your data. So maybe T is some test statistic. Based on the data. And the test is if T is bigger than C, reject H naught. So this probability up here would be so you given alpha, you want to find C so that this probability is alpha. You know the null distribution typically. You know this test statistic. You know the distribution under the null distribution. So you can find this. So suppose you see some value the observed value is T, then the p-value of that observation is determined by this. Okay. You can also say it this way, the p-value is the probability of an outcome for the test statistic at least as extreme as the observed one as the observation little t. Okay, so you think of little t as being sort of an extreme situation. What's more extreme would be capital T bigger than little t. Okay. All right, so these are two equivalent formulations of the p-value. P-value is a probability of an outcome for the test statistic at least as extreme as the observation. And it's the smallest alpha for which the hypothesis would be rejected under a given observation. So you collect your data, you formulate your test statistic, and then you can talk about the p-value of that data set or of that test statistic. Now, there was a nice example in exercise that I assigned. Maybe you went over it in the discussion section? No? Which number was that we went over with the z of alpha over 2 and there was a normal? 28. Number 28. Okay, it's number 28. You probably all did this successfully, or maybe not. So I won't ask for a show of hands whether you did it successfully. I'll just bore you in case you did, and hopefully enlighten in case you couldn't. Suppose a test statistic t has a standard normal distribution. If the test rejects the null hypothesis for large values of absolute t, what is the p-value corresponding to t equal 1.50? So you collect some data, and you formulate your test statistic. It turns out the test statistic has standard normal distribution. And you see this. This is the value of your test statistic. What's the p-value of that observation? So the p-value, again, is the smallest significance level at which the null hypothesis is rejected for that observation. So under what significance level would cause us to reject the null hypothesis if we see that? We could also view the p-value as the probability of an outcome for t at least as extreme as the observed value of the data or of the test statistic. So what's the observed value of the test statistic here? What's this t? It's 1.5. So what's the probability of an observation at least as extreme? Well, this would be the observed value is at least as extreme as that. We reject for large, so extreme would be larger, right? So this is the p-value. Okay, and this is normal random variable. So what's the probability that that happens? Well, guess we have to look in a table. Table 2. Table 2 says what? If I look up 1.50 in table 2, I get the number 0.9332. Table 2 says so what would this probability be? Oh, I'm sorry. 1 minus this. 1 minus that. A little detail there. 1 minus this. The table 2 says the probability of capital T is less than 1.50 is 0.9332. So the probability is bigger than 1.50 is 1 minus 0.9332, which is what? 8 here. 660 point, I think, right? So what would this probability be? Yeah, because what is this probability? It's the area under the normal density to the right of this point. We want the area under the normal density to the right plus the area under the normal density to the left of minus 1.50. So this thing is giving us that area, which we found to be 0.0668. But we want also the possibility of being out here, which would also have this area 0.0668. So the probability of being out here or out there would be the sum of those or twice that. So the p-value is 0.1336. Okay, so that's the value at which, the p-value at which that observation would be rejected. Any question on that? We'll do a couple more examples today with p-value. In particular, we'll talk about Fisher's examination of Mendel's data and breeding of peas. He had a p-value for his data of 0.99996. What would it mean if the p-value of a test is 0.99996? What's the probability of getting a result more extreme than that? 0.99996. So 0.99996. 99996. So that's so 99,996 times out of 100,000 you'd see data more extreme than that. Only 4 times out of 100,000 times would you see data better than that, or it's suited. So what does that mean? It's very unlikely to have an observation with a p-value like that. Extremely unlikely. Yes, he was a monk. Perhaps he had divine intervention. Though there is a possibility that we don't know what came up, but the book mentions that it's possible that he performed his experiments until the results looked good. In statistical tests, you should fix a number of trials, do those trials, and then do your test data. He might have performed the experiments a random number of times until it looked good. I mean, this is early on, and people didn't know about scientific methods or statistical methods. So if that's true, like suppose you were going to test a coin for whether it's fair, and you toss it until the number of heads is equal to the number of tails. And you say, well, it's fair. That would be about what a similar situation, where stopping at a time when you think the data look right. Okay, so let us return to the generalized likelihood ratio test. Did I assign problem 15 and 16? No? I should have. Try those problems. Try problem. In fact, there'll be another assignment due, let's see, the problems 33, 36, and 39. Did you get my email? Yes. Okay. Loud and clear, huh? Okay. So for the next assignment, hand in that on Monday together with 15 and 16. Okay. So it shouldn't be too hard. Or would you rather hand it in Wednesday? Okay, Wednesday will be fine. Hand it in when you come to take the final. I'll post an assignment today. Okay, so turns out that minus 2 log lambda has an approximate chi-squared distribution where the degrees of freedom is the dimension of the parameter set capital omega minus the dimension of the parameter set omega naught. So as the number of observations increase, if n is the number of observations, as n goes to infinity, this gets closer and closer to that. The distribution of this gets closer and closer to chi-squared with that many degrees of freedom. Okay, so Last time did we talk about multinomial at the end of the class? I forget. It was my notes, but I don't remember if I covered it. Did we talk about the MLE for multinomial? Well, brief review then. I think I did. Yeah. So for multinomial, we can consider whether the probabilities in a multinomial are given by a one-parameter family of probabilities. For example, in Hardy-Weinberg equilibrium, the Hardy-Weinberg equilibrium for these genotypes is of the form, the frequency of genotype capital A is 1 minus theta squared. The frequency of capital A little a is 2 theta 1 minus theta, and of little a is theta squared. So it would be this, and then you might want to say here, so the hypothesis here would be theta is equal to theta naught, where P, well, no, it's this. Okay. So here's theta, some parameter. Here, theta would be between 0 and 1. So in this case, omega naught would be the interval from 0 to 1. And capital omega would be this set here, set of vectors with m components, non-negative, they add up to 1. What would the dimension of this set be? Well, let's consider the dimension when m is 2. When m is 2, If I were to draw a picture of that, well, in the P1, P2 plane, what would it look like? Omega is that line segment, and its dimension is 1. Why is it dimension 1? Well, if you know P1, that's one dimension, right? This says what about P2? 1 minus P1. So there's really only one free variable here. What if we did this in 3 dimensions? Picture here in P1, P2, P3 space. It's that triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. And what dimension is that?
2.
That's a 2-dimensional thing. Why is it 2-dimensional?
Yeah,
Right. P3 is 1 minus P1 minus P2. Right? So once you know P1 and P2, P3 is determined. So what's the dimension of this for general M? M minus 1. And dimension of omega naught is, that's a line segment, so it'd be 1. Though in this example, in that example, dimension of omega naught would be 1. But it could be a k-dimensional set. So let me just say it's some number k, but less than m. In the Hardy-Weinberg example, k is 1. All right, so this lambda up there would have this form. Okay, so what are the x's? And what's little n? Okay. And did we compute the MLE for multinomial? Let's quickly see why PJ hat is the MLE for the multinomial. These observations are fixed or given, and we want to find the P that maximizes the probability density of the evaluated at those observations. I think we did this maybe over a week ago. So the multinomial probability density looks like this. Yeah.
X1 through Xn on the left hand side, right? Is it F?
Oh, yeah, M here. Thank you.
No, I meant it should be N in both cases.
Where?
You should change the N for that, right?
Here?
Yeah. It should
No. No, N is the number of observations in their M cells. So for example, in the Hardy-Weinberg, the cell 1 is the genotype A, capital A. Cell 2 would be the genotype capital A, little a, and cell 3 would be little a. So their M would be 3, and you could have any number of observations, maybe 1,000, 10,000, something like that. Yeah. Okay? So again, we have to maximize over a n-1 dimensional set. What's the n-1 dimensional set? Omega, right? Should I call this omega sub m here? And if we take the log of this and maximize, do we find the same location for the maximum? Yes, because the log is an increasing function. And the log is nice because converts this awful thing with products into something with sums. So we want to maximize And if you remember from your 2D or 2E, I forget, when you're maximizing a function, multi-dimensional function subject to some constraint, you look to see where the gradient of the function is parallel to the gradient of the constraint. They should point in the same direction. So we need to find P such that the gradient of L is a multiple of the gradient of G. This is called the method of Lagrange multipliers. you remember it now? No? Okay. So the gradient of L well, the gradient is just the vector of partial derivatives. And dl dpj is equal to xj over pj, right? If we differentiate that with respect to pj up there, what happens to the log of that multinomial number there, n choose x1 through xm? What happens to that when I differentiate with respect to p? That's 0 because it's a constant as far as p is concerned. When you differentiate that sum with respect to the jth p, the other ones disappear. You just get the jth one. Derivative of xj log pj with respect to pj. What's xj times derivative of log pj with respect to pj? It's 1 over pj. Okay. And what about the gradient of g? That would be this vector where we put g here. What's the derivative of g with respect to p1? And with respect to p2? Yeah, they're all 1s, right? Okay. So this condition here says what? This must be lambda times the jth component here. So the equation xj over pj equal lambda holds for j equal 1 up to m. Okay? That's what this says. If you find a vector pj so that pj over xj is always lambda, then you found the place where the maximum occurs. And what does this say? How do we find lambda? We find that x1 over p1 equal x2 over p2 equal equal xm over pm. Okay. Or I guess I could also say xj is lambda times pj. Maybe it's better to look at this. Okay, this must hold for all j. That holds for all j. So what happens if I add up this side in j? No? What do we get? x1 is the number of observations in cell 1. x2 is the number of observations in cell 2. xm is the number, it's n, total number of observations. If I add up this, I get n. If I add up this, what do I get? Lambda, because they add up the p's, what do you get? 1. So if I add up this, I get n. Add up this, I get lambda. So this says that n is lambda. Okay, so all those fractions are equal to n. And I wanted to solve for the p's. So how can I solve for the p's in terms of known quantities? I know how many observations there were. I know how many observations fell in cell j. So pj would be xj over n. So that's the MLE for multinomial. Okay, so that's why it's there. So returning to that lambda up there, We can, of course, cancel the multinomial coefficients and combine the denominator and numerator under the same product, because each term here in the product in the numerator is raised to the xj, and same thing for the terms in the denominator. So I can write this as pj at theta hat over pj hat raised to the xj. And I want to use this fact here. So I take minus 2 log lambda. Okay, when I take the log of a product, it becomes the sum of the logs. What's the log of this thing? Well, an xj comes down, I get log of what was here. And now what's xj? I want to express that in terms of the pj's. Xj is pj hat times n. And I don't know if you've taken a course where they mention entropy. Ever taken a class on that? This is the relative entropy of pj hat with respect pj theta hat with respect to pj hat. This is a term that comes up in information theory. But you don't need to know that. Okay, so let me write here Oj equal the observed frequency in cell J, or proportion in cell J. Which is pj hat. And Ej is what you expect. That's pj of theta hat. That's the MLE. You have a model in mind. For example, like the Hardy-Weinberg, you found the theta hat, which is the MLE, and your null hypothesis is that this is the frequency that you should have. But you took a sample and you observed this one. Of course, the sample one is not always equal to the one in the whole population, right? We know that from sampling. What's your favorite ice cream flavor?
Ice cream.
What's your favorite ice cream flavor?
Mint ice cream.
Mint. So from that, can I conclude that everybody here prefers mint over all other? No, right?
No.
So the observed frequencies aren't always the true frequencies. Mint is good. Okay. Okay, so we can rewrite this then. Minus log lambda would be minus what? Summation minus 2 sum j equal 1 to, oh, this should be, I made a mistake here, m here. and m here. So if I absorb the n with the pj hat, well, let's see. No, I'm sorry. So I should get 2n. Okay, so I'm sorry, not the observed proportion, but the observed number, which would be n pj hat equal to xj. I'm sorry, not the observed proportion, but the observed number. So it would be the proportion times the total number of observations. So if I absorb that n with the pj hat, I get the observed observation oj, and then I could rewrite the log by multiplying top and bottom by n ej over oj. Observed times log expected over observed, sum n minus 2. And this would be chi squared, have an approximate chi-square distribution with dimension here's the dimension of omega, it's m minus 1, dimension of omega naught, the parameter space here for the theta is k, so it would be dimension of m minus k minus 1. Okay. Now, some people prefer polynomials to logarithms or quadratic functions to logarithms. So they come up with an approximation to this. Now, how could you approximate this? Now, if you have a lot of observations, like n is large, you'd think that the observation should be close to the expected thing. In other words, this ratio should be close to 1. Okay. So log of 1 is close to 0. So you might be able to use a Taylor expansion for this. So this function has the form x log something over x. But there's a minus sign here, so let's look for a moment at this. X log x over x naught, where little x is playing the role of O, and x naught is playing the role of E. But there's a minus sign here, so if I put the minus sign in past this logarithm, what would it do? It would reverse this, right? So I'd have O log O over E. I'd have x log x over x naught. I want to find a Taylor expansion for this around x equal to x naught. Okay, so this is our function f of x. What's f prime of x? Well, let's see. That's, I think, made a little easier if I do this. And now, differentiating this term, I differentiate that, I get 1 times log x. Plus x times derivative of log x is x times 1 over x, or 1. Then here I differentiate this, I get minus log x naught. So what's f prime at x naught? If I put x equal x naught in here, I get log x naught plus 1 minus log x naught, which is 1. Let's do second derivative. I have to differentiate this term, and that's just 1 over x. So f double prime at x naught is 1 over x naught. And so the Taylor expansion for f of x out to order 2 looks like that. F of x naught was 0, right? I didn't say it, but what is f of x naught? X naught log x naught over x naught. X naught over x naught is 1. Log of 1 is 0. Okay, so the first term is 0. Next term, f prime of x naught is 1. And then this next term, I get x minus x naught squared over 2 x naught. Okay? So this says that minus 2 OI log EI over OI, or OJ. Let's stick this. Is approximately equal to that's right. Is it EJ minus OJ EJ minus OJ? Let's see, X is the OJ, right?
Yeah.
OJ minus EJ plus OJ minus EJ squared over 2 EJ. OJ is the X, EJ is the X naught. Okay. OJ is X, EJ is playing the role of X naught. Okay, so now what happens when and the minus 2, what happened to that? Remember, I absorbed it by reversing this. The minus sign got absorbed by reversing this. Now let's put this in that sum. Oh, I'm sorry, this should have a 2 here, and this cancels that. I forgot to multiply by the 2. And the 2 cancels this. Okay, so this looks kind of nice. It's just linear terms and quadratic terms. What does this add up to? Well, let's go back and look what OJ is and what EJ is. Here's OJ. If I add up these numbers, they're n times pj hat. What happens when I add up this in j? What do the pj hats add up to? 1. So the OJs add up to n. If I add up these, what does this add up to? Well, this is a probability vector that adds up to 1. So I get the EJs add up to n as well. Because the pj theta hat is just the probability vector that maximizes the likelihood that depended on theta. So if I add up these, I get 1. So if I add up n times those, I get n. If I add n times those, I get n. So this first term is n minus n, or 0. Okay, so the net result is that this thing has an approximate chi-squared distribution with m minus k minus 1 degrees of freedom. This is called the Pearson chi-squared statistic. advantage is that you can compute it pretty directly. You don't need to take logs of anything. Just take difference in observed and expected values squared divided by this, add them up. So let's take a break and come back and we'll apply this to a couple examples. Here we expect that the null hypothesis is that the distribution is like this. We should find the theta hat. And I think we did that last time. Or do I imagine that we did it last time? We did it? Okay, good. So I can write down what the theta hat is, or Pj of theta hat. Theta hat so this is Hardy-Weinberg. We found, yeah, I'm pretty sure we did that. It's theta hat, the maximum likelihood estimator for theta hat is twice the number of things in cell 3. That is, what's cell 3? It's this, cell 1, cell 2, cell 3. So little x3 is the count of this genotype in the sample. X2 would be the number of this genotype. So theta hat is twice x3 plus x2 over twice the number of observations. Okay. So in the book, they give an example. And the blood types were labeled capital M, capital MN, and capital N. And the observed numbers were 342, 500, and 187. And N here is 9, 12, 10. If I add up all those, do I get this number? The expected, this is O, E equal expected counts. Now what would the expected counts? Well, the expected counts are N times the Pj theta hats. So what are the Pj theta hats? Well, if this is theta hat, what's P1 of theta hat for this model of the Hardy-Weinberg? There'd be 1 minus theta hat squared, right? P2 of theta hat is twice theta hat, 1 minus theta hat. And P3 of theta hat is theta hat squared. Okay, now we have given the observation, we have a value for theta hat, right, which we can compute. We're given x1, x2, x3, right? So here's x3. Here's x2. We multiply this by 2, add it to 500, divide by n, that'll be our theta hat. That's theta hat. Huh. Oh, thanks. Okay, so then we can compute P1 of theta hat. P2 if theta hat, and P3 if theta hat, right? This would be n times P1 of theta hat, or it'll be 1,029 times this. And that gives, when you do that computation, 340.6. This number would be 1,029 times this number, where you substitute 874 over 1,029 in here. And what you get when you do that is 502.8. And similarly, 1,029 times P3 of theta hat is 185.6. So using Pearson, where the linear term cancels, we just get this. So we just put in these numbers. This is E1, O1, E2, O2, E3, O2, O3. We just form this combination of that table there, and I think you get 0.0319. Because what's the difference here? The difference here, this minus this is 1.4, right? The difference here is minus 2.8. The difference here is 1.4. If we square these and divide by the E values, we just add those up. And that's what goes here. Yeah?
The data hat, is it 2 times 1029 in the denominator?
Oh, yes, it's 2 times that. Sorry. Yeah, 2n. I'm sorry, I forgot the 2. So this would be 2058. Okay. Yeah. But I did give the correct values though for these data. Thanks. Okay, so if you were to form a test for the hypothesis that the Hardy-Weinberg equilibrium holds based on this statistic, when would you accept, when would you reject? You would accept if the observed values are close to the expected values under the assumption, right? You would accept if they were the observed values are close to the expected values relative to the size of the expected value, I guess. If the expected values are really small, why would, if the expected values are really small, then you'd want the observed values to be really close to the expected values. If the expected values are really big, this kind of adjusts for the possibility that the expected values might be really small. Then you'd want the observed values to be even closer, right? So you'd want this to be small, then you'd accept. So the test statistic might, this test might be reject H0 if x squared is bigger than some level c. Okay. So if we have a desired significance level, well, what significance level would you like? Pardon? 5%? Okay, you're a statistician already. According to the book, that's the traditional choice. We'd have to find C. So that the probability that x squared is bigger than c, so I'm assuming this is under the null hypothesis, would be 0.05. But under the null hypothesis, this is chi-squared with how many degrees of freedom? Yeah, in our case, theta is a one-dimensional thing, right? And how many cells are there? M equal 3. So this has dimension 3 minus 1 or 2. This has dimension 1. So 2 minus 1 is 1. So it's chi-squared with 1 degree of freedom in this example. Okay. So you look up at the table, the chi-squared with 1 degree of freedom line, and you find, I think it's table 3 perhaps, or yeah, table 3, it's the first line. I think it's 3.84 is C. C is 3.84. This is chi, yeah, question.
Oh, sorry. Can you repeat how you got 1 degree of freedom?
Oh, okay. So how many cells are there? There are cell 1, cell 2, cell 3. So there are 3 cells. That's the M. M is 3. Okay. And the general probability vector for a multinomial with 3 cells would be P1, P2, P3, with P1 plus P2 plus P3 equal to 1, right? So that's a 2-dimensional thing. Remember the little triangle? So the dimension of capital omega is 2. And the null hypothesis is that the distribution of the p's look like this vector, 1 minus theta squared, 2 theta, 1 minus theta, and theta squared. That's 1-dimensional. There's only one parameter there, theta. So the dimension of little omega naught is 1. And so this is dimension 2, because it's 3 minus 1. This is dimension 1, so 2 minus 1. Is that clear?
Yes.
Okay, good. Okay, so this is the, in the table what they show is the probability chi-squared is less than or equal to something. So you look up where's the C for which probability chi-squared is less than or equal to C is 0.95, right? 1 minus this. And that number is C equal 3.84. Okay? So what's the p-value for this observation? Well, that's the probability of seeing chi-square, Pearson chi-square statistic at least is extreme. That means P would be the probability that chi-squared with 1 degree of freedom is bigger than 0.0319. Okay? This would be more extreme than that. Okay? The probability of seeing something more extreme than this. And for that, that would mean that this is 1 minus the probability that the chi-squared is less than 0.0319. And you can approximately get that from this table, I think. 1 minus let's see, 0.0319. That's, you have to look across here, 0.0319. Well, that's not something you read off from the table. Because they jump from chi-squared 0.1, the probability that you're less than something is 0.1, to the probability you're less than something is 0.9. And there's a big gap in between those. So you'd have to go to a better table, or you could convert this to a question about normals. How could you convert this to a question about normal random variable? What is a chi-square? Square of a normal. Chi-square with 1 degree of freedom would be the square of just one normal random variable. Chi-squared with 2 degrees of freedom would be sum of squares of 2 independent normals, etc. So this would be, I think we could resolve this by saying what? This would be 1 minus the probability that and I think the normal table is better probably than the chi-squared, where z is normal with mean 0 and variance 1. And this you could look up in a table. You could figure this out from a table. How would you figure this out looking at the normal table? What do they tell you in the normal table? They tell you probabilities like that, right? So how could you get a probability like this? Or you know how to do it. I think we've done this before. So this I think you could look up. And that would be the p-value for this experiment. And I think they actually, in the book, tell you what the p-value is. Yes. .86. So does that give you a comfort level with the null hypothesis, or a bit of discomfort? Or you don't care? Or you don't know? What does it say? You ran this experiment 100 times. 86 of those times, you'll see a chi-squared, Pearson chi-squared statistic bigger than this value. So does that mean we're kind of close or not so close between observed and expected? It means we're close. It means that usually you see something more extreme than what you just observed. So you observe something that's really close or confirms your null hypothesis. If you check this 100 times, 86 times, you'll see something that's farther away than what you observed. So what you've observed is very close to what you expect. So that should confirm your null hypothesis that the distribution is according to this with that theta hat. Large p-value means that you usually see observe things more extreme than what you did actually observe. Okay? And the larger the p-value, the more often you see it, more extreme things. Now you could do this with with this as well. but the computations are a little harder. These computations you can do with your hand calculator. You could also do this with a calculator if you had a nice one, nice enough to do logarithms. The calculator on my computer, you know, that little icon, I think just does multiplying, dividing, adding, and no logs, no exponentials. So on a very rudimentary one, you can do this. Actually, you can do this by hand, right? You don't, well, in principle. Okay. So that's the advantage of the Pearson. In this case, the Pearson and the minus 2 log lambda are very close to each other. And they both have the same distribution. Okay, so what about Gregor Mendel? Oh, by the way, so do we accept, if we have a diffidence level of 0.05, do we accept here? What do we find C was? We reject if x squared is bigger than c, where c is 3.84. What observed value did we see for x squared? 0.0319. That's less than 3.84, so it's well within the acceptance region, right? Way below the acceptance value, I'd even say. So we accept the null hypothesis here. So it looks like Hardy-Weinberg were correct. Okay, so what about Mendel? Mendel bred peas, crossbred peas. Okay, now according to modern genetics that been developed since Mendel, the expected frequencies or numbers should be 312.75, 104.25, 104.25, and I see I didn't write down the last number here, 31, and 34.75. Because the frequencies should be 9/16, 3/16, 3/16, 1/16. So it would be, what's 9/16? That'd be a 1 minus theta should be 3/4, theta should be 1/4. So theta squared, 1 minus theta squared is 9/16. The frequency here should be 1/16, and then the frequency of these combined should be 2 theta 1 minus theta. And if you multiply those frequencies by the number of observations, you get these numbers. Okay? So from genetic theory, we expect it should be like this. And these are Mendel's data. Okay? So we can form the Pearson and also the minus 2 log lambda test statistics. Using this table, if you plug in the numbers, this becomes 0.618, and the Pearson chi-squared test is 0.604. Okay, so E and O have what meanings? This is O1, E1, O2, E2, O3, E3, O4, E4. Plug those numbers in the expression here for minus 2 log lambda. You get this. If you plug those numbers in the Pearson chi-squared statistic, you get this. Now these are supposed to be observations from a chi-squared with 1 degree of freedom. What's the p-value? So for this, we'll compute the p-value. Probability that chi-squared with 1 degree of freedom is bigger than 0.604 is 0.9. So 9 times out of 10 you see results more extreme than this. In other words, where the observed values are further away from the expected values as measured by the Pearson chi-squared are bigger. So from here, this line to this line, this means a random variable now with chi-squared with 1 degree of freedom. Here I'm saying that the observed value of that chi-squared statistic turns out to be 0.604. In general, what's the probability that a chi-squared with 1 degree of freedom is bigger than this? It's 0.9. Okay. So Sir Ronald Fisher collected all of the data from all of Mendel's experiments, viewed them as being independent of each other, and in each one you get a chi-squared statistic, and what's the distribution of sums of independent chi-squares? If I have chi-squared with m degrees of freedom and a chi-squared with q degrees of freedom, what's the sum of those two if they're independent? What's the distribution? Chi-squared with m plus q. Why? What's chi-squared with m degrees of freedom? Is a sum of m squares of m independent normals. Chi-squared with q degrees of freedom would be the sum of squares of q independent normals. If I add those normals together, I have how many squares of independent normals? M plus q, so it's chi-squared of them. So he adds them all together, he gets a chi-squared with a big degree of freedom. And he computes this Pearson statistic. And then he computes the p-value. And the p-value he found was that. Which makes his results a bit suspicious. Okay, I mean, no casting, no aspersions on Mendel. It was great that he did that, but there must have been some flaw in his method. It could be he threw out data he didn't like. he might have thought that's justified, or as it mentioned, he might have performed his experiments until they matched what he expected. Which there were certainly the standards we have now have been developed in the time since he did this, and he was a pioneer. So, but anyway, it's interesting that, or else he was really, really, really lucky. Okay. Okay, so good. I think that was interesting. Let's the next section in the book in chapter 9 is called Poisson dispersion tests. And this is developing tests. This is using the generalized maximum likelihood ratio. I'm not sure I'm saying the words in the right order, but test to decide whether things are distributed according to a Poisson distribution. So one example in the text is bacterial counts. You have some glass plate here, and you spread a sample of milk across the plate evenly, and then you come back and later you see bacteria spread out there. Is a distribution of the bacteria Poisson? Or another example is counting asbestos fibers on a filter. And there are many other examples where you might want to try to decide whether the distribution of particles on some plate, or maybe did anybody watch the football game last night? Okay, so it was delayed, right?
Yeah.
Why?
Rain and thunder.
Well, thunder's not going to hurt anybody. Lightning. Unless you believe in Thor. Lightning, right? Lightning strikes in the field. So just think of having some mark off some plot of land, and then wherever lightning strikes, you count where they are, and as a distribution of lightning strikes in the field, Poisson. So there are many, many examples where you might think that the distribution is Poisson, so you should develop a statistical test for Poisson. So, for example, here, you might partition this plate into squares of equal area. And then you sample some of the squares, and you count how many bacteria cells you see in each square. So you'd observe x1, x2 through xm. This is the xi is the number of bacteria in cell or square I. And you want to know, are these observations from a Poisson where the parameter is the same for all squares? Or are the observations from a Poisson where maybe the parameter changes from square to square. Same thing here with lightning strikes. Maybe the intensity of lightning strikes is different in different parts of the field. Perhaps there's a lake in the middle of this square of land that you've set up, or maybe there's a city in there somewhere, or maybe there's a river or some woods or a barn or something like that. So this test is to decide whether the counts are from a Poisson with the same parameter for all squares or different parameters for different squares. So you, again, should look at capital lambda equal to the maximum over lambda in some set omega naught of the likelihood function of your observation value at lambda over So this is the likelihood where the parameters in different squares might be different for the Poisson counts, and the numerator is where the parameter is the same for all squares. Okay. Now for omega naught would be the interval from 0 to infinity, the possible range of parameters here. So the dimension of omega naught, it would be 1. And the alternative hypothesis is that there are different parameters for each square, and that would be in R. That would be in Rm. That would be our set omega. And so here the dimension of omega would be m. And so minus 2 log lambda would have a chi-squared distribution with m minus 1 degrees of freedom. Dimension of capital omega minus dimension of little omega naught. Okay. Find the maximum in the numerator, I can just find the MLE for Poisson. And the MLA for Poisson lambda hat is x bar. Okay, so it's just the average of the observations. So in this case, it would be the sum 1 over m so that's under the hypothesis h naught. To find the maximum in the denominator, well, lambda j is just x. Lambda j hat is just the observed count. Well, this is what we expect, right? And this is the only thing we have to tell us what you might expect for the number of particles in cell j or square j. It's xj, so that should be the MLE. Okay, let's call that lambda j not hat but bar. So capital lambda after factoring out this common stuff, looks like this. Okay. So just keep in mind likelihood of lambda would be the product e to the minus lambda xi, lambda to the xi over xi factorial, and likelihood for lambda 1 through lambda m would be product like this, but you'd have lambda I here and lambda I there. And the xi factorials cancel when you take the ratio, and we know what where this is maximized, we know where that's maximized. And we plug in the values lambda hat and lambda bar j, and then replace lambda bar j by xj, lambda hat by x bar, and this is what you get when you simplify everything. So minus 2 log lambda would be minus 2 xj sum j equal 1 to m log x bar over xj plus what? Take logs of this, what happens? You just get the numerator. And what happens to this sum? When I sum up the x bar, m times I get m x bar, or just the sum of the xj's. When I add up this, I get the sum of the xj's. So what happens to this term? It's 0. So that's gone. Okay, so that's that one, and the Pearson chi-squared you could also compute. But I'll leave it like that. So I guess I'll stop here today. Next time we'll apply this to some data about asbestos fibers on a grid and bacterial counts. But there's not time to go through the numbers.